Okay, so I tried to play a bit with the variadic template class, and so I was used to do header and .cpp file.
Yep.
And is it possible to do the same when you do the variadic class, or do you have variadic template class, or do you have to put everything in the same file? Couldn't find a way of separating this.
When you include, when you use templates, you have to have the code available in a translation unit. So the translation unit is basically the whole file that contains all the information. In that case, when you use templates, you have to include the file. You can't split the header and the CPP file, but you have to include the header before CPP in order to have all the possible code available that will be compiled. So it's still possible to split CPP and header files. Actually, it's a good idea to do it sometimes, but the inclusion. But the inclusion has to provide the old code there. I guess it's because my microphone was on the back and the sound was bouncing to my back. That's why the Larsen kicks in. So having different object files is more difficult. Basically, you must have the primary templates. You must have the recursion going, and the compiler must know what that is. I don't know if that answers your question, but yeah, templates exist only when they are instantiated, right? So that is why you need to have big translation units when you work with template code. Usually, you start including a lot of files. Maybe the volume is too high. Okay. There is a concept in C++, which is the header-only libraries, in which you never have you never link against that library. You never call the linker. You just include all the headers. And you compile your stuff. So many Boost libraries, for instance, like this. The meta programming libraries are like this. They don't have a runtime component. And you usually have a single CPP file and many header files. Then you compile an object file, but the interface is exposed by that object files, not contains the templates, because the templates are only instantiated for that case. There are proposals to be able to do that, but I don't know where they are going. It's called the modules. For C++, that basically would allow you to compile, to have like the templates available in an object files. Intel compiler had this technology some time ago. I think they kind of dropped it. This is called the precompiled headers, which you can have. You can precompile the templates, but it was really cumbersome and not very easy to use. Other questions? Okay, let's start then. This morning we start talking about the move semantics. Who never heard about the move semantics? Okay, so almost everybody have heard at least about this concept. How many of you are familiar with move semantics? Okay, few people. The idea of move semantics is that it can be slightly confusing if it's not approached in the right way. So I'm trying to approach it in the right way. Let's see if I succeed. So somebody might have seen this scheme which classifies C++ expressions based on the type it has. So before C++ 11, there were two kinds of expressions. One was the L value, and the other one is the R value over there. As I was mentioning yesterday, the L values are the ones that could stand at the left of an assignment. And so it's like a variable, right? You can assign to that variable, or it can be a reference because you can assign to that reference. An R value is something that can be on the right side. And these include variables and the reference actually, but it includes also things that cannot be modified, like constant variables, like number 10. I write x equal 10, I don't write 10 equal x, because 10 is R value, it cannot be on the left side on the assignment. So R values are things that can only be on the right side of an assignment. With the introduction of C++ 11 and the introduction of move semantics, still things got more complicated, getting to expiring value, to pure R values, generalized R values. Why this is needed and why this is not really impacting your life is because of move semantics that will deal with these things internally. But sometimes you can find an error message from your compiler in which this thing shows up. But basically what the R value was before now is PR value, is a pure R value. And X value is something that is going to expire, something that is going to disappear very soon unless something happens that will keep that thing alive. A little bit about references. As we said yesterday morning, references are not objects. It is a compound type that are not objects. You cannot have arrays of references. You cannot have pointers to. You cannot have references to references. So that is what a reference is. It's just not an object. And to indicate the reference, C++ uses the ampersand, which is a tref. You can read the tref. And it's basically specified to, it's used to indicate an alias to something else. So if I say int ref x equal y, x becomes an alias for y. They will basically point to the same thing. Implementation-wise, a reference is basically a pointer. Only that you cannot dereference it. It will be automatically dereferenced every time. So C++ 11 introduces R value references with the double ampersand, which is here. The idea of R value reference is that you can have a reference to something which is an R value, and something which is supposed to have a temporary lifetime, like number 10 or an object constructed on the fly. And this extends the lifetime of your object. So before, the only way you could do it before R value references was to create a const references, like in this case where const tref x equal 10, and that was allowed. you have a reference which is constant to this number, and you can pass x around, but x is constant, cannot be changed. So if I do x++, then I get an error message. Now, with trefref, then you can really do assign to 10, and you have a reference to an R value, and you can even change its value and say x++, and that is okay. You can use that thing. So why this thing happens and why it is specified this way, well, it's really not because of this. No one uses R value reference to extend lifetime something. And I find this a little bit confusing. In fact, what really this trefref is meant for is to be used in overload resolution. Okay, this is the real thing. This is why this is actually useful. It participates in overload resolution. So when the compiler looks for the function to call, it will have also this rule to sort out. Let's see an example of this. So on the left side, we have a function f, which takes a reference to an integer as an argument, and we have another version of it which takes an R value reference instead. Now the main is calling is calling f with two different arguments. The first they call f with x, and x is a variable, and x will call the reference version of f, as we always as we all know. But f of 10 will call the intrefref, the R value reference implementation of f. Now, 10 is just a temporary value. It is created in this place and passed to the function. And after this function has been executed, that object doesn't exist anymore. If I, instead of putting 10 here, I will put like a construction of some object, like std vector or something, that std vector will be passed to the function, but after that function call, that object will be gone. It's actually destroyed. So when you have a temporary object that is created on the fly, this binds to an R value reference. And when you call the function, if the compiler finds a version with the R value reference, then it will call that one. In this particular case, if I didn't have this guy, if I didn't have the R value reference implementation, this will give me a compiler error, because this is a constant value and I cannot have a reference to a constant value, so I cannot call f and I get a compiler error. I should have here int constref in order to be able to do it. So this is the main idea. We can do a specialization, we can do overload using R value references to bind objects that are created on the spot, and not, but not only, as we see very soon. So now we have the another syntax which I find very interesting, even though I never seen used in practice, is the fact that you can have you can also decorate your your member functions with ampersand and ampersand with the R value reference. And then when you say, when you create an object of type A and then you call a.callMe, you go to the reference implementation. And when you create A on the fly, so you construct A on the fly and then you do call me, then you go to the R-value reference implementation. It is just to point, if you need somehow to specialize with these cases. This decoration here is in the same place where the const for member function has to be placed. I guess everybody knows, but I think I feel I should remind that a member function which is not static, even though it doesn't accept any argument, is actually a function requiring one extra argument all the time. And this extra argument is this pointer, is the pointer to the object itself. So this guy, this reference, this ref, or the const, is the qualification to the this pointer, is the qualification to that hidden argument. This means then this is a function that takes a pointer to A, which is a reference, or this one is a function that takes a pointer to A, but is an R-value reference. So now when I create this guy, this is an R-value reference, and I will pass it through the call me, and so I will go to these overload. Yep. Whoa. Go ahead.
For example, on the left, if the first method would have been declared as constant reference, which one would you choose?
That is compiler error.
Okay. It would be ambiguous.
Pretty sure it will be ambiguous. I'm not sure though. Let me check. Yeah, I'll try it. Now it's time to show off. Okay, so let's write a simple example here. So let's just check that this compiles. Yeah. Now let's put const ref here. Yeah, it compiles. So the const ref binds to the reference, and the other one binds to the R-value reference. Yeah.
You just have int f, int x.
Okay, that is going to be a conflict sometimes. Okay, if I do like this, I take x by value, and all the functions bind to it, and the compiler would not know what to do. That is a compiler error, and it tells you that this is ambiguous in all cases, basically. But yes, so the ref and the const ref bind to L values, and the ref binds to the R value reference, to the R value. Now, if I remove this, let's remove this one, which is wrong, but let's remove also this one. This will keep working, right? This is just regular old style C++. These all work. Now, the const ref and the ref are two versions there, but the ref is more specialized for the case of R values. So this guy will work with compile, right? And all the versions goes to that thing. Now, Oh wait, that is a very stupid mistake. All right. So now if I run my application, I see one R value, which is the second one. You can actually check it out even better. You see R value and R value. But if the second one is not present, if I don't have this one, this guy works again. It just takes these 10 as a const reference. All right? So this one is more specialized. There was other couple of questions.
Yeah, can we go back to the slide with the class and the method understand?
This one. Sorry, I have the presentation. Okay, yeah.
Not familiar with the construct. Does it mean that this is the pointer when I declare the first method?
No, so let's put it here, right? Okay. Okay, let's look at this code, right? What this means? What the compiler does here is the following. The compiler will create a function somewhere, like a regular C function, which is called call_me, and it will create this guy with this syntax. It will be like void, because it doesn't return anything. Call_me a pointer, and you call it this, and that's it. Actually, is integer pointer reference. Right, it would be like this. Something like this. Okay, this is not real code. This is just show you what happens. When you put a const qualification here, if I do a call_me with a const qualification, which you all know, means that the function is not modifying its data members, for instance. This will mean that the compiler will create a function which is a const pointer. It's like this. Is a const before pointer or after. I always have to try. But anyway, this is what the function looked like. In the case of the R value reference, the actual function that will be created is something that looks like this. So and this is a these. Inside your member function, you can access these. These is actually an argument which is passed to the functions in real life. And this const qualification, the reference and the ref are actually just the qualification of the type of that first argument. So the way you could see at it is simply say, if I call my member function, if I call my member function with an object which is an R value, because it's just a temporary, then I will bind to the this that is an R value, and I go to call this function. And it's just for overload resolution. Otherwise, this is a reference. This is just an object. It has a name. It exists. So I will go to the reference one. Does this explain or not?
But if I also write a method without the ampersand, just void only.
Yeah, that's just a regular one. Yeah, and pretty sure it should work. No, we can try if you want. We can try to see. It should work, yeah. Without the ampersand, you don't qualify your object. It becomes like a value, I think. It might give you actually ambiguous overload error, because now this is passed by value, which is probably the same problem we had before. So I guess this is going to give us a compiler error. If I do like this, yeah, call me cannot be overloaded. So if I put here explicitly a reference, then it compiles. So similar as before. So it makes sense. I like this. I like the ability of specializing for art values and al values. I always looking forward for possibility to use it, but so far I had no chance to use this kind of thing, so I don't have first-hand experience. But the mental model is the one that we just said. But these being able to overload with R values really is the thing that allows to implementation of move semantics, and also to have move-aware functions like a pushback in a vector. As we say yesterday, moving means to, instead of copying an object, instead of doing a deep copy, as it is usually referred to, instead of a deep copy, we can do like a shallow copy. We just take the data member, instead of copying all the heap allocated storage, for instance, we just copy only few things, but we have to remember to set up the other guy and to keep the other guy in a consistent state. But moving means stealing the guts of some object, honing that guts, and releasing the other guy from honing that things. Let's see how a movable container look like. This is a plain old-style C++ class. You have a class which is called movable. It has a pointer to int stars. So somebody pointed out that I am a computer scientist because I'm using always integers. Yeah, you got it. I always use integers everywhere. But anyway, I have a pointer to integers, which I set to null pointers just to start with, and I have an integer which store the size of my container. All right. Then I have a constructor which takes the size and instantiate the new pointer with a new statement, and then I will have the size to be instantiated with the value of the size of the storage. All right. This is so far. The third line should be fairly easy. Let's move to down here to the to the copy constructor. When I do the copy constructor, I have a signature like this that I have movable that takes a movable, which is a constref, and some other object called other, and I say if the pointer is not null, then I delete the current pointer that I have. I allocate a new pointer and associate a new size, and I copy the other as the SD copy of other object into my new pointer. Okay? Something wrong? No? Like, no, I was saying.
I was surprised by the copy syntax, if you want.
Well, there are. There are occasions in which I want to copy, right? So that is then you copy then you call the copy constructor. Now upstairs here, in the second constructor is actually the move constructor, and the signature of the move constructor takes the movable object as our value reference, our ref, and this does only 4 instructions. First of all, it takes the pointer of the other object and assign it to itself. Then set the pointer of the other object to null putter, and set the size of this object to the size of the other object, and the size of the other object will be 0. So now after this move happened, the other container will be like a default constructed container, which has null pointer and size 0, and the new one is this guy. So if I do main, in my main, I can do a movable z, and I create on the fly this movable of 200, which create a movable object of size 200, and then I initialize this with z. This will go to the move constructor. So the move will take the pointer and the size of the newly created object and steal that information and set the other guy to 0. Now, it's not really necessary in this case to set the other guy to 0 because, well, this guy is anyway gone after this instruction. But there are many cases in which I want to steal the guts of something, but I want to keep the guy alive, like in this case. So now I take z that I created here, and I do std move of z. Std move is just a little wrapper that return an R-value reference type of this guy. It does basically a static cast to R-value reference of this guy. And this goes again to the move constructor. But after this, z will be empty, and u will be the new object. And the new object is done without doing a copy, without deep copy. So first of all, we have to know is the move constructor, which when you have this signature is called move constructor. It's important to keep the other object consistent, otherwise you get into weird errors, and we'll see some of them. And now we can see the performance that we have here, the performance implication. Here we have a linear algorithm to do the copy, linear with the size, and here it's just a constant time operation. So this movable created on the fly is called a temporary object, and it's also called an unnamed object. It doesn't have a name. It is created, it exists for a short time, and then it will go away. In order to call the move constructor, you have to use std move, because the std move basically is telling the compiler or the language to say, I don't want this to be moved. Okay, I would need z later on maybe, but I don't need it to contain the information that it contains right now. So just take whatever is in there, pass it to the other guy because I don't care anymore. And the question is, we need a destructor for this class? And we think we need a destructor. Yeah. Of course we need it. We need it because we have a new statement. So you have to delete your storage. But we need it also for some other reason. And it's the fact that these, so the destructor, okay, now we are setting a null pointer here. So the destructor is needed because you have a new statement. So we need to free our memory. Otherwise, we have a memory leak. It's interesting that if we didn't do this null pointer here, and we add our destructor, then we had a runtime error at the end here because this guy was not a null pointer. Basically, we had two objects pointing at the same storage, and the destructor will have freed twice the same storage. So we'll have a runtime error, which is double free error. So the destructor is needed because of the new statement, but also the move constructor needs to put these null pointer on the other object. Otherwise, you get a double free error message at runtime. In this case, when the program finishes, everything looks nice, and then you have this error that appears on your screen. Let's implement the same class, but now the data member inside our class is just an std vector. So instead of having a pointer and size, we have just a vector. Now this is much shorter code, bigger fonts, and we have a constructor who takes the size, we instantiate my vector v with that size. We have a move constructor, and we have a copy constructor again. Now, to implement the move constructor, now we have to write here the v, my vector, is the other v, but it has to be moved. Do you know why it has to be moved explicitly? Exactly. The idea is that when I'm outside my function and I do movable and I create this object on the fly, this is an R-value reference. It's something that doesn't have a name. But when I'm here and I'm R-value reference, which is extending the lifetime of the object. So now the object exists, it has a name, right? This is where the extending lifetime comes in. So now other as a name, it is a temporary object, it will not exist after this statement, but it exists in this context or in this scope as a named variable. So it exists, it is a reference, and so you need to say std move of the other, because you're telling that, okay, I'm really doing moving here. I'm really doing move construction. So I need to move this guy here. In the copy constructor, I would have to write v_other.v. That's simply calling the copy constructor with the other guy. But you see, if I wrote other v without std move here, this will be exactly the same code. It will just do a deep copy and not to move. Accidentally, the code might actually work exactly as it was working earlier. It just slow. Or it might behave very, very weirdly because the guy is never, because without the move constructor, the other guy is never reset to an empty container.
So the previous code would be now considered unacceptable, right?
The previous code is considered, yeah. I can repeat. So the previous code, yes, it is. It can be considered unacceptable. Because it requires you to write more code, so it requires you to maintain more code, and if there's a bug, you have to chase it. This one is much shorter, so much easier to maintain, and it will work. Plus, so this container, the vector, is move aware, so it can be moved, right? It has constructors that has been implemented and tested to actually work. So now we need to do std move, and now the question is, do we need a destructor for this class as we needed before? And the answer is that no, we don't need a destructor. The default destructor that the compiler will generate for you will go and destroy the data member, which is move aware, so it will just free his memory if he has to free his memory, otherwise it would not. So this code is actually not only shorter, but it's actually more correct than the one we wrote earlier that actually was not right because it has a leak. This is an instance of using the RAII, the resource acquisition is initialization, in which we use inside our classes RAII-aware containers. So vector gather the storage that it needs when it's constructed somehow, and then it release it at the end. And our class using these as a data member doesn't have to do anything because everything is taken care by the data member itself. So exploiting these things helps you writing safe code and with very little effort. But let's move on. Let's consider the same code as before, right? We have a vector as a data member. We have our constructor. We have the move constructor. You have and we delete our copy constructor. If we delete the copy constructor, we're saying, I want this object to be move only. So I can only move my object, which means I can do all these operations. And I create my movable of size 200, move it into Z. I create I move Z into U, and now what I expect in the output is that this size will be 200, this size will be 0 now because I moved Z away, and now U size should be 200. If I now notice I put printf, so like our output inside my constructors because I want to check what happens. I want to check what happens in here. And now the output that I got from this code is the following. So is there something wrong with this output?
It seems that the compiler optimized the way the construction move of the first statement.
Yeah, exactly. So D is movable. This move constructor to construct Z is actually never called. So if we investigate a little bit more here, we need to understand why the compiler is allowed to do something like this, because my move constructor is supposed to do something, has some side effects, right? It prints something on the output that is a side effect on a global variable. Now, suppose we remove all the constructors. We keep only this guy here, only the constructor with the size. And we run the same code, then the output is this one. Of course, the move constructor doesn't print anything because there's no move constructor. But actually, it's happening. Right? The move is happening anyway. So we see the V size is 0 and the U size is 200. So this code behaves exactly as the other one. The compiler introduced automatically the move constructors, the copy constructor, the move assignment, and the copy assignment for you. And is actually doing exactly what you wanted to do. So this is actually a better version of the code that we wrote earlier, where we explicitly wrote our move constructor and our copy constructor. Well, this is really all the code you need to write to implement these containers. Just 2 lines of code. Let's go just back here. Right, this guy, we wrote this guy, and we wrote this guy. This is exactly the same code the compiler would generate for you if the move constructor and the copy constructor would be left to be automatic. Now, we are here, and we see that the move happens anyway. So something is telling me that the compiler is using some default constructed move constructor. So we go back to our stuff, and we put, this is exactly the code that we had before, but now we are copy constructing W with Z, and now we see that it's actually calling the copy constructor, it's calling the move constructor here, but still I don't see the move constructor happening in this statement here. So what I want to try to do is to delete explicitly the move constructor and also the copy constructor, and just run this statement and see what happens. So what should happen here? Should it work? Should the compiler do something here or not? Who thinks this code works? Who think it doesn't work? Who thinks, I don't know. So we saw before the move constructor was not called, right? It was just, the compiler was just doing something, magic. It was doing the thing. But this was because the move constructor was defined. So the class is move aware. The compiler says, oh, listen, I can move this thing. Let me be smarter than the user, than the guy who writes the program, and implement it as fast as I can. So if you compile this code, you get this error message. Use of deleted function movable ref. So even though it's not called, the compiler requires it. This is one of the rare cases in which the semantics percolate through the language and tells you, okay, you need to be, if it is a move constructor, it is supposed to move. It's not supposed to do other things. It's a move constructor. And if you construct a class that has a move constructor, then the compiler assumes it can move. So if you put a side effect in your move constructor, like the std out, the stdc out that we had before, that the compiler feels free to do everything it wants. It can ignore completely and can take this guy and construct directly on Z. Should be clear, right? So this is semantics. The move semantics is called like this because this is just the meaning of this guy. We usually think of C and C++ programs as machineries that you use to implement something. Like, the fact that a function as a signature doesn't have a meaning, right? It's just a function call. It happens to look in some way, but it doesn't have any meaning. In this case, it has a meaning. The compiler requires that meaning to be actually implemented. And I don't know if this is a good thing, but this is how things are. Let's go see a real world example, or almost real world examples. We have an input stream from the keyboard, and until I type the word end, I keep writing strings on my terminal, press enter, and I want these strings to be pushed into a vector of strings. So I have a vector here, a vector of strings. You can find the example in your folder, the full running example. And so we basically, I'm writing, but I'm actually typing. So I'm typing my string on screen. I click, I hit the enter button. It will write the string that I just wrote, then push back this string into the vector, and then prints the string after these pushback. Instead of doing a pushback of input, I do a pushback of std move of input. If I do pushback of input, then I do a deep copy of that string, and then I copy the string into a vector. So the vector creates a new string and makes a deep copy of that string. and then the new input will overwrite the old string, and everything will work as fine. The result will be exactly the same. But if I do std move, then the pushback as an implementation with R value references. So the pushback for the vector has two signatures. One takes the const ref value, so it takes the reference to the object, and the other one takes an R value reference to the object. So when I do std move of input, this is actually moving the string into the vector. So the only copies the data members of the string, set the input string to a null string, and then it goes on. So after this operation, when I print what's left, I get the empty string. Is it clear? Should I run it? So two signatures, two overloads. The one selected is the one with the R value reference because I'm forcing it. I'm saying this input, I want to cast it to an R value reference. This will call the move constructor inside. And so the input will be empty, and I copy only. And I do like a shallow copy inside the vector. Now, in real life, this is probably not going to change anything in this particular example, since I will not write long strings on my keyboard. And there is something which is called the short string optimization, in which implies the string never allocates any storage on a heap. But if the string is long, then it will allocate something on the heap, and then, so having a copy or having a move can really make the difference here in terms of performance. Any question? Now, we have seen that the move is kind of subtle, right? The compiler can ignore the fact that the move is happening. But it's not only that thing that is subtle. There's something else. Let's have our movable, the now as a vector, as a data member, and also an integer that stores the size explicitly. Right? And then I want to construct my movable with the size, and I instantiate my vector with the size, and I instantiate my size with the size. And now I do the code exactly as before. So I do movable z200. Actually, I construct z with 200. It doesn't matter to move it or not. It's not calling it. And then I move z to u. And now I want to show the size. And now what happens is that if I print z dot v size, this gives me 0. And if I print z dot s, this print 200. Anyone wants to explain what's going on here? So the move of z into u leaves z v dot size, or the vector size, to 0. V as being correctly moved, but my size data member is still 200 here. The trick is that trivially movable objects are actually copied. If I have an integer, a float, a char, when I move it, I just copy it. And why is that? Is that because if I have an integer which is 100 and I want to move it into some other integer, well, first of all, performance-wise, it will be actually more efficient. You just copy the value into the other one. And second, I don't know what value to set to the other integer. Is 0 a good value to put? Is -1? Is this max size? What is the value I should put when I move it? So the compiler doesn't even know what to do here. It depends on the user semantics, what the value is. Yep?
But then u.s is also 200?
Yes. The move happens. The data member is moved. U.s is 200. The move happened, but is not resetting the other guy. Actually, the other guy, z, is probably now in an inconsistent state. Interestingly enough here, it is an inconsistent state because we were not very smart in writing this code, because we have the size in the vector. There's no real reason to keep the size as a data member. One might say, well, but if I have it in a data member and I implement my size member function in movable, I just can return that size. I don't need to query the vector for the size, right? An implementation for the size will be movable.size is implemented as go to return v.size, which looks like another function call. While if I return s, there's no function call involved. That is more efficient. But it's not true. Size will be a const method. The compiler knows how to optimize it. It will inline everything, and you would never see any glitch of performance penalty there. So this as data member doesn't make any sense. It just introduces redundancies because we have twice the same information in this structure. And having redundant information simply leads to unexpected results. So if you implement a size member of this movable class, you can just return v.size. And that doesn't have any performance implications. It will be as efficient as just reading data member. So the actual code for this class will be simply movable as the vector, movable as a single constructor, and the methods that forward the calls to the inner data member. What happens when we use R-value references and templates? So what happens here? I have a function, which is a template function on a type T, and my function foo accept a T ref x. And okay, here is just an example. I want to ask you what type x is. If I do decl type of x, what is the type of x? And I have three cases here. The first one calls f of I. The second one calls f of int ref. So I explicitly saying the type of that guy, explicitly saying that T is an int ref of I. And the third one is foo of 42. So let's see what the type is in the first case. So what is the type of x in the first case? Is an integer? Who says an integer? We have integer reference, integer R-value reference, the three options. What do you think should happen in the first case? The thing is for integers, integer reference, integer R-value reference. Good. Second case, I'm forcing it ref. Okay. Let's go for the first case first, all right? Actually, let's go for the final solution. There is one thing that is implemented as Okay, which is specified in the standard. I don't remember the name of this thing. Collapsing, yeah, reference collapsing. Thank you. Reference collapsing is that if I have a tref and I pass a t here, which is a reference, this will make t ref and will be transformed into t reference. If I have a t reference and the reference will be transformed into t reference, our reference will be t reference again, and the t ref will be transformed into t ref. Means that foo int will be seen as a reference to an integer here. Actually, this is it's a little bit of a trick, because if I write just a template function, t will be int, right? It will not be an int ref. But this is just a named variable. It exists. This will be bind to int ref. And int ref will be ref. So in the first case, decal type of vex will be a reference to an integer. In this case also, I'm forcing it to be int ref. So this will become int ref, right? I substitute t with int ref. This becomes this case. With then x will have type t ref. And for the case of 42, this is our value reference. This will become t ref followed by another ref, and this is going to be kept our value reference. That this x in this case will be an R value reference. I think that everyone that's seen this thing for the first time said, these guys are crazy. Why they're doing this thing? They just hate us so much. But it makes total sense after a while. Maybe a long while, but after a while it makes sense. This rule allows the implementation of something which is called a perfect forward. We have a function bar that takes a reference to x and increment x, and a function bar that takes an R value reference to x and doesn't do anything. After all, it's an R value, who cares? It will be dying soon. No one cares about this value. I will kill it. I will not do anything in this function. So this might be like an optimization, if one. You have an operation to do if it is a reference. If it is an R value reference, I don't care. But now I have an intermediate step. This intermediate step is the function foo. So the user never called bar directly, will call foo. And foo we call exactly as earlier. So we call foo with I, with the interf I, and the 42. Now with the same signature as before, but now I call bar with the std forward t of x. This will maintain the referencelessness of x. So that if decal type of x is t ref, then x is a ref. Otherwise, it's just a reference. Right? It applies that simple trick of collapsing that was seen earlier. That if, in the case of foo42, you go to here, x is a R value reference. You take this R value reference as you forward it as R value reference. And we'll call the bar without the implementation. In all the other cases, x will be an int ref, and we'll call the actual operation. And we'll change the value of x. Let's make an example. Suppose that instead of std forward here, I will put std move. What would happen? Std move cast the type of x into an R value reference. So we'll always call the thing without an implementation. So if I'm passing an R value reference to this guy, if I pass a reference to this as a type, if I do std move, this will always call the empty implementation and will always get the wrong answer. And if I'm passing an heavy object, because for an integer it doesn't probably make much sense, but if I'm passing a heavy object, passing by reference, I move that object somewhere, I call this, I move into here and I don't do anything. I probably lose my object. While std forward keeps the referenceness of the incoming object. And it is very, very, it's very useful when you write code that has to forward the call to something else. So the user gives you a function to call and gives you the data. And if you want to call the function with that data, and you have to keep the referenceness of that thing, otherwise you get the wrong result.
Even though the signature is t-ref-ref-x, the compiler somehow still knows what the type was.
Yeah, it's applying. Yeah, that is a kind of a trick. If it is an I, or if it is a name variable, or if it is an R value reference, he knows where it came from. And then t become an int reference instead of an integer. It's very simple trick, but it might be a little confusing. If I didn't have the ref here, t will be an int in this case. Ref say, okay, it has to be some reference, a reference of some kind. So if it is a reference with it coming in, just keep a reference, otherwise put an R value reference on it. Yeah?
What would happen without the forward? I mean,
without the forward, X is a reference.
Why is it a reference? I mean,
yeah.
before you showed that X is not a reference, like that X depending
Yeah,
on
yeah.
what is
Exactly. Yeah. Remove the, okay, suppose that this is tref instead of ref. Okay, so you want this to remove the R value reference from here?
No. I
No.
want to remove the forward.
The forward. Okay, good. We remove the forward and we call it with X. Now, X in here is just a named variable. It exists as an object. Bar of X would just call this guy here, always. You will never call the R value reference.
So
Even though this is...
that X is a ref.
Absolutely. It's like the move constructor that takes the other object and you need to forcibly move it in order to do the move. Otherwise, it would not do the move.
Okay, so I always, like if I want
Yeah.
to call the
So it is an R value reference coming in, but now you're assigning a name to it. It is alive in the scope of your function. It's not an R value anymore. You can assign to it, you can change it, you can do whatever. It exists. So if I don't put the forward, I just call bar of X, and X is an integer, even though it's an R value reference, but it's still an integer, and I call the bar interf. Is it confusing to anybody else? I guess should be. Okay. Yeah. So why do I need to do std move here? I'm passing an object which is temporary, created on the fly, or I'm saying I want to move the object. I received other with R value reference. So it should be that when I do v other dot v, that other is an R value reference I should be moving.
Well, yeah, but I mean in this case
It's exactly the
other dot v. So I mean I have
yeah, it is
I have to
deferred. Yeah,
what other dot v should be.
but actually it's exactly the same issue. It's actually the same thing. Other exists as a name here. It can be used as any other variable in your scope. So you need to, if you want to move, you need to explicitly saying it. Similarly,
As you receive an R value reference,
Basically, yeah, you can think like it as a mental model that is what happens. You receive it as an R value reference, but then it behaves as any other integer, even an integer reference. Right? If you receive an integer reference as a function, you don't even know it is a reference inside your scope. You treat it as just an integer, right?
So because there is no transitivity in C++, right? So
Sorry, can you don't use the mic?
it happens because there is no transitivity in C++. So if it's a const, doesn't get const when you call another function. If it's a ref, doesn't get ref if you call another function. So there's no transitivity.
Yeah, exactly, yeah. It belongs to the function, it's called to the passing arguments to the functions. Right? It's how the arguments are passed to the function. So yeah, if I don't put the forward, I will always go to the. If I don't put forward, I always go to the x++, and I will increment the value. I will have 42 at some point inside my function here. After this bar, x will be 43. It can be accessed, can be processed, and everything. So after this one, if I don't put the forward, if I put the move, I always go to the R value reference implementation. And x will never change. So forward keeps the referenceness, and when I call functions, when I forward these arguments to somebody else. I have one example that might look a little scary at the beginning. Let's say I have a main, and I want to run foo with two arguments, 4 and 5. Foo is a function that takes two integers, right? And I also have a struct bar, which has the function call operator. So I can construct bar, and I want to call that object as a function passing number 6. Actually, this should be an integer, a function with an integer. So now I have this is a function. The bar is called in this case a function object, is a functor. So whenever I have an object of type bar, I can call it as a function because I call the operator parentheses on it. So if I call bar an object of type bar parentheses 6, I will call this operator. And foo is just a function. I want to call the function with 4 and 5. Now the problem is that one is a function and the other one is an object. So I might be more efficient if someone passed me a function object instead of passing me an actual object. For instance, I might assume that the objects that are passed to me are actually stateless, so they don't contain any data members, and I want to do something special. So I have two implementations of deduce and run. Deduce and run will do, in case I receive just an object f, which is just the first argument, like bar in this case, and a sequence of arguments, whatever number of arguments it is, this is a periodic template. Then I want to, instead of passing the object, I just create it on the fly because I know it is a stateless object. I create it on the fly and I call the function call operator on it. And if it is like a function pointer, so I'm expecting something that returns something that takes a certain number of arguments and is a pointer to function like foo. So foo is a pointer to function. And a certain number of arguments, which is in this case 4 and 5. Then I want to call just f without construction. I don't want to construct the object. I just want to call the function with those arguments. Now, if I do something like this because I want to dispatch differently my functions, this happens actually quite often when you write abstract code. You have to take functions, you have to pass it pass them around, you need to call them later on, and you need a way to know that, okay, these functions receive arguments by reference or by value, or by our value reference, and you cannot write all the possible combinations here, otherwise the code explodes in size. It becomes so big that you're never able to manage it. So instead, you have two lines of code, two simple functions, and using std forward, you can call any function the guy passes in, maintaining the referenceness. So if it is a foo int ref instead of foo int, then you will keep the reference of the object. You will get an error here because I'm calling the function foo with a reference to an R value. But this will work. So the std forward keeps that referenceness and forward the argument to the next guy. So when I do a foo, when I call with foo, I go with that implementation that matches because it's a function pointer. And when I call the bar, I call the other implementation, which construct the object on the fly instead of passing it around. It's quite a silly example, like almost all examples that you can make C++, but it is a pattern that you can find often around. Questions? So I suggest to go for an early break. We can start at 10:20 instead of 10:30, and then I can start from there.